5 winning principles for better design. My name is Cliff Medling, and I'll be your host. We're going to jump right in as we have a lot to get started in just 22 minutes. It may go a little bit longer than that as the first one did. We have a lot of good information. Before we get started, just wanted to mention a couple things. If you look at the Go-To webinar panel here, this is the View Full Screen button to toggle in and out of full screen. We recommend you view in full screen mode. Also, if you have any questions during the presentation, be sure to answer them in the question field here, not in the chat area. Also, we're going to have a few poll questions that pop up on screen. These are multiple choice questions that you can answer very quickly, and that'll keep the presentation very interactive. And we will download you will be able to download a recording of the presentation probably tomorrow, as we are recording this presentation. So let's go ahead and actually go to the first poll question. You have a couple options here. And we're really just curious, do you spend more time designing in 2D or 3D? So basically, if you spend more than 50% of your time in 2D or in 3D, select one of these two answers. And while you're answering that question, I wanted to go ahead and introduce our presenter today, Mark Snyder. Mark has been with SolidWorks over 17 years now. He's been around. I think there's only a couple other people I know that have been here longer. And he has been involved in our industry longer than that. Mark creates a lot of technical content for all sorts of videos, tutorials, and many other items that you have probably seen if you've been in the SolidWorks community for any amount of time. I like to call him one of our SolidWorks gurus. And if you've ever been to SolidWorks World, you may know Mark as the guy who runs the Model Mania contest, which has been going on for many years now, like 14, 16 years now. 15. 15, okay. So Mark is going to discuss 5 winning principles or strategies for better design. Please note that there's a lot of good strategies out there, but these are some that five that Mark felt were very important at the top of his list. So if you have any other principles or ideas, feel free to add them to the questions, and we'll maybe we can come up with another webinar. So let me just show you these quick results for this first webinar. For this first poll question, 85% said they spend more time in 3D, which is good. And with that, Mark, it's all yours. Thank you.
Okay, thanks, Cliff. One of the things I want to do, or when I was assigned to do this presentation, I thought it'd be an interesting topic just to understand, what is design, and how can we leverage the existing tools that are on the market, namely SolidWorks, to make our design better. And visiting lots of customers over the years, I've run across many different people who use varying levels of our product, and I always note the ones that are the most efficient and the most productive, and those are the ones who use some of these principles that I've kind of gathered here today. So what is design? This is my definition. It's a creative process that leverages a concept or idea, specs, parameters, costs, and available manufacturing process to achieve a designated objective. Pretty straightforward. Lots of things that go involved, but it is a very, very creative process. I like to think of it as a very creative process. It's not like a detailer who's just laying a bunch of lines, or a 2D guy who's just laying a bunch of lines and arcs to represent geometry. You're actually designing and creating stuff. So some questions I always ask when I'm designing: will it work? How do I know if it's going to function? There's many ways that we'll address that in the presentation. Can it be manufactured? How much will it cost? How am I going to sell it? All those things kind of are things you need to think about when you're designing any kind of product. So these are my 5 strategies for better design. Number 1, capture design intent. It's very important that you capture information, every bit of information as you go in your model as you create it. Simulate your performance. So how do you know whether or not the part is going to function properly? The best way is to use many of our simulation tools. Cost of manufacturing should be something you think about whenever you create every feature. It's something that you should be thinking about. I think there are a lot of people out there who have a lot of experience, and this stuff comes natural to them, but SolidWorks has some great tools for junior designers and engineers who maybe don't have that experience. If you've ever been drug out into the shop by a machinist and said, how am I going to cut this part, or how much it's going to cost to cut this part, you'll realize real quick, you gain that knowledge real quick from getting drug out in the shop. Refining your product. I think change is good. You know, a lot of people have problems with change in maybe other parts of their lives, but change when you're designing is really a good process. You need to continue to refine and iterate your design, and you come up with much better products. And one of the benefits of 3D design with SolidWorks is that you are able to quickly make those design iterations, but you also need to manage them. So you need to have tools that allow you to manage that. And we do that with SolidWorks Enterprise PDM. And then leverage your model downstream. The people that I see that are most productive are ones that take their models and use them for marketing, photorealistic renderings for marketing, or product manuals using 3D Via Composer, or CAM, leveraging cutting your geometry straight off of your 3D model, 3D printing for rapid prototypes, or any more 3D printing for production parts. And automation, people that have highly configurable parts and they want to let either a salesperson or maybe customers just actually run through a selection process and choose that using some rules-based engineering tools. So those are my 5 bullets, if you will. We'll start off with the capture design ideas. This is probably the most important one to me. It's very important you capture your design ideas. Anything from the napkin sketch, get it into 3D, and then create production drawings from that. So I think that's, you know, pretty straightforward, but you've got to be able to capture that information. So we'll walk through some of these things as we go through. Design is one of the biggest things about design is most designs are copied from, in some way, from some existing design. So you just took something, maybe you made it better, maybe you made it lighter, maybe you made it, you know, meet your customer's requirements. So you've got to be able to leverage legacy designs. That could be existing 3D designs or existing 2D designs. So we'll walk through real quick how you can leverage 2D information in SolidWorks. Design intent, one of the most important things. You've got to capture robust design intent while you're designing so that your model behaves in a flexible manner. And then embed intelligence in your model. The customers I see who embed the most intelligence into their model. I mean, something as basic as applying material to a part. It not only adds the color to the part, but it also adds the density to the part, so you can calculate mass. So you get all of your material properties for simulation. So all of your mechanical properties are all available there. Leverage that type of information, like description and numbers and whatever, for bills of material and title blocks and PDM. All that stuff, put it in once, use it many times. So let's talk a little bit about design intent. Design intent is the arrangement of features in a part such that downstream changes react in a predictable and flexible manner. Pretty straightforward, but you have to think about how you want your part to behave. It also is something that you need to consider when you're working in assembly. So part-to-part relationships in assemblies is also important. It's also part of design intent. Some questions you should ask as you're designing a part or an assembly. Say, should a hole stay centered on a part? Should it remain a fixed distance from a certain face or edge? Should it move with other features? You got to really think about all the possible changes that might come down the pipe. You're never going to get them all. Trust me, you'll never get them all. But the more you build your model to behave as you intend, the better off you are. This is very important. Design intent does not have to match your manufacturing dimensions. It can. Some people choose to do it that way, but I think what they do is they limit a little bit of how their parts behave when they want to make those changes. So your design intent dimensions can be different from your manufacturing dimensions, and we'll walk through that. And these are concepts that really aren't applicable in 2D. It's not something you do. In 2D, you're laying lines and arcs that represent your parts. In 3D, you're actually modeling parts and you're putting parametric intent into them. So let's do a quick little demo and show a little bit about what we're talking about. So what we're going to do for this demonstration, since Cliff was only giving me 22 minutes, I've already chewed up 9 of it. So we're just going to kind of do a little bit of work on this little tooling clamp for our miter saw. It's a quick release clamp, allows me to get my workpiece in and out real quick. So let's jump over to that one. So this is our design. Pretty simple, pretty straightforward. Kind of move things around. You can see how it would behave. Talk about how we started. One of the most important things with being able to use a 3D tool is collision detection, interference and collision detection. We have interference tools which are great, but collision takes it to a next level because it allows me to move. It allows me to move my item through its range of motion and then actually see how it's going to behave in real life. So as I move my model through here, you can see that when I come down here, I actually get a collision. So these faces here that are highlighted in blue actually collide. Now that's actually tucked back in there around the round part of this part here, and that's something I really probably wouldn't have found in 2D. It's not something you can see, and obviously this is a very simple example here, but I think you'll realize if you use the collision detection tools and the interference detection tools, just how powerful these can be for coming up with valid designs as you're going through, and in this case, trying to just understand the range of motion. So we got this nice assembly here, and it's got my little tooling clamp and everything that I have, my hold down clamp. How did we come up with this? So one of the ways you're able to do this is to leverage existing information, and this information was something that was an idea. It was a napkin sketch. So in this case here, all I did was inserted the sketch picture into a sketch, brought that sketch picture into a sketch. I scaled it to the size because I knew the distance between here and the center line of that was going to be about 140 millimeters. Once I had that in there, I was able to create kind of a stick diagram of this sketch right here. So I just sketched this out, just trying to mimic this sketch that I had. Drew this out, just trying to mimic the imported sketch picture that I had, and then threw some dimensions on it that kind of made everything behave and work as I wanted it to. So this is the way I wanted it to go. Once I had these rough dimensions, I was able to go off and start building the parts that I needed to create my geometry. Now I mentioned a little bit earlier that one of the nice things about working in 3D and doing good design is being able to reuse existing information. A lot of people have 3D information that they can leverage and reuse parts, but not everyone understands that they can easily leverage their 2D information as well. So I'm just going to walk through real quick a kind of a scenario here where I can leverage an existing 2D DWG file. Now I could open this up directly in DraftSight, but I'm going to choose to open it up straight in SolidWorks. DraftSight is a 2D only tool that allows me to maintain existing 2D drawings or create new ones if I want. I'm going to bring this into a sketch. We'll add some dimensions, and maybe we'll turn off some layers, and we'll bring that in. So what this does is it brings in what looks to be 2D information, and it is, but it's in a 3D environment. So I want this to be my front view and this to be my top view. So SolidWorks has some great tools for allowing you to leverage this data. So I'm going to say that's my front. Turns gray. I'm going to say this is my top. Now watch when I hit this button, it'll actually fold down into position. So that folds down into position, and then I have my top view. If I look at from the side, you can kind of see they're not lined up. Well, let's go ahead and do that. We have a great tool to align these two items here. So now when I jump to the top view, I can see that I'm lined up with that bottom view. So let's turn it into 3D. How do we do that? Let's take this original sketch right here, and we'll extrude it. So I got that. I can drag it out here, maybe measure that distance of that line to figure out how deep it goes, or just click this item right here, and it gives an up-to-vertex relationship. And that's all I need to do to create the first geometry. Now I need to put a hole on the top up here. I don't know what size it is, so I can just measure this using the SolidWorks measure tool, 12 millimeters. So that's a 12 millimeter tapped hole is what that is. I'm going to jump to a top view here. So I wanted to line up right there on that point, so let's just go ahead and leverage that point using the hole wizard here. I'll call this in my machinery's handbook of all my hole types. I don't have to look up sizes, tap drills, counterbore size, any of that stuff. I have all my standards here, all my different hole types here, all my different sizes here. In this case, we'll take a 12 millimeter tapped hole, and I'm just going to position it right on that vertex of that existing one there. So I just lined it up with that one, and I'm done. So there I have it. And just a couple of clicks here, I was able to take and rebuild and recreate that 2D part and turn it into 3D. Now we want to embed some rich content along with that. One of the ways to do that I talked about is material. So we can choose from a vast library of materials, or these are my favorites here. I'll just go ahead and make that plain carbon steel. You might want to put some other information into this part, like description or numbers or stuff like that. And these are just custom properties. So SolidWorks allows us to create a custom interface for doing this. So I can put in whatever I want here, and then put in I can't type and talk at the same time. new block, whether I make this or buy this. All this information is fully customizable. It already knows what material because it's extracting it out of the part. Therefore, it knows the weight. So we'll go ahead and apply that. So I've added that information to our part, and now we'll just save it. I'll just give it a, I don't want to call it that one. Call it block 2, something like that. We want to get this information, leverage our 3D models in drawings. How do we do that? Make a drawing from our part. It's very simple, very easy to do with SolidWorks. Front view, just project up a top view, automatically drops in my center lines for me. If I want to insert any dimensions I used to create the model, I can go ahead and bring those in, or maybe add some additional dimensions here as I go onto my model. So very quick and easy, I'm able to kind of leverage the 3D part and turn it into a 2D drawing that I can then use for manufacturing. Remember, we added some custom properties like the title, new block, gave it a name, all that information. Its weight is carried across here as well as its material. So you want to customize your templates so that they're able to extract this information. You only have to enter it once. Enter it at the part, leverage it in the title block, leverage it in the assembly drawings as well. So let's take a look at the assembly drawing for this one. So there's our assembly. Let's go ahead and open its drawing. So it's got all the information from that assembly that we had. But more importantly, all the information that was typed in about each part gets done automatically. So I don't have to do anything here. This bill of material is generated automatically for me, and it also comes up with a quantity as well. So it's kind of nice capability. Now, one of the other things I talked about was design intent. So let's take a look at this part here, and we'll just discuss design intent a little bit. Very similar. This is the exact same part that was in the image that was in PowerPoint. So I have this dimension 140 here. It goes to this center line. What's that center line? Well, that's the center line where that threaded rod comes through for the clamp down rod. That's not important for manufacturing, but it's important for my design intent. You also notice at this 24, I have a dimension for the width of those two holes, but I don't locate them from this center line, and I always want it to be centered. Well, if we zoom in here, you'll see that there's a symmetric relationship between the center line and the two holes. And you'll see that as I make changes of that, it grows in the way that I want it to. You also notice for this guy right here that there's a horizontal relationship between that midpoint and the center of that one. So I don't have to add a dimension vertically to control that. I want these holes to always be centered between those two items, and that way it'll stay that way. So let's take a look at how some changes might be made when we deal with that. So let's take our 140. I just want to drag this out. Notice that all these holes and the end move with it because the way I have my design intent captured here. The 6 millimeters, I need always 6 millimeters from the end. So I can set this back to 140, something like that. Likewise with this 24, I can go ahead and change that and bring that however I want. We'll undo that change. Oops, that's fine. And then this one here, you remember I had my design intent was to keep that hole centered about that boss. Well, it's very quick and easy for me to be able to do that as well and get that in there. So those are my design intent dimensions. That's the information that I wanted for the design intent. But for manufacturing, they need different information. They don't care about that center line. That's a theoretical center line that doesn't mean anything to them. So the important point is don't force yourself to compromise your design intent just for manufacturing, because you can always add these manufacturing dimensions down the road. In fact, since this is a sheet metal part and it actually has a little jog in here, the flat pattern is the best place to locate those holes anyway, and we'll locate those from the central location, which is the far left hole. Everything will be dimensioned from there. So like I said, don't worry about trying to, or use your design intent appropriately as opposed to letting the manufacturing dimensions control your design intent. We'll go back to our PowerPoint here. So those are just the first topic, which is design intent. Secondly is in simulation. We got to know how our part's going to function. Is it going to perform properly? Is it going to perform safely? Is it going to fail? Is it going to break? SolidWorks has many tools. SolidWorks simulation for structural thermal fatigue and vibration. We have rigid body motion analysis. We have computational fluid dynamics. Injection molding simulation with SolidWorks plastic, and even environmental impacts using SolidWorks sustainability. So we'll do a quick little simulation, or show you the simulation that I ran on this one, just to give you an understanding of how that goes and how easy that is. Now, one thing that I find, with some customers, not all of them, we have, especially in the last seminar that we did earlier this morning, a lot of people are using simulation, which is fantastic because it is easy. And a lot of people shy away from it. Maybe they didn't study enough FEA in school, or they weren't exposed to it, or they send their FEA out to have done it. SolidWorks provides tools that allow you to do this natively right inside of SolidWorks on your SolidWorks model. So let's go ahead and take a look at a simulation I ran here. This is fairly basic simulation here. I didn't do a whole lot. I held this surface down here, and I applied a load of 30 pounds over on this side here, and then I go ahead and run my simulation. So let's do that. The nice thing about this is SolidWorks knows all the parts. It knows all the materials for the parts. It's able to know how those parts interact with each other, and then it goes through and meshes it and runs it. In about 10 or 15 seconds, we will have done a SolidWorks simulation on this part to understand how it's going to behave under load. Now, what it does is it comes back with my stress information. So these are my stresses. Some people might say, well, I don't understand what those stresses mean in comparison to, whether or not the part's going to fail. Well, that's fine, especially when you're listing out stresses here and you have parts that have different materials. Different materials mean different yield strengths, different strength requirements for each of those. So one of the nice ways to be able to deal with that is through a factor of safety plot. Factor of safety compares the calculated stress for each part and its material to its yield strength of that part's material. So then you come back and it says, okay, here's all my factors of safety. My lowest factor of safety is 1.65. Maybe my design requirement is that this thing doesn't fail at 1.5. Maybe I need to beef things up and say, hey, I need to increase the strength of some of these parts so that it can withstand more load. Those are all design considerations you can take. But the nice thing about it is that this is very easy to do, and you can do it directly inside of your design environment. For those who aren't comfortable with it, one of the great ways to do it is just to do what I call an A to B study. You take something like this link here and you simulate it with one, say, thickness or one material, and then you do it with some design changes and say A is better than B, B is better than C, and you come up with a better design that way. So those are some things I think that everyone should be using the various simulation tools that we have available. Next thing I think you need to think about during the design process, and this is something you need to think about the whole time, is how much is this part or this model, this assembly going to cost? How much am I going to be able to manufacture it? Can the shop machine this thing? If you've ever been dragged out to onto the shop floor, you're going to appreciate some of these things, because believe me, it's happened to me. So SolidWorks costing uses customizable templates to check your costs of your parts, and you can compare those against your targeted costs. The nice thing is you can run through the different design iterations or change materials and then compare the costs based on that information. Again, the templates are customizable, so you can control what goes in there, what your machining costs are, what your labor costs are, and so on and so forth. DFM Express is designed for manufacturability. It goes through and runs a check based on a certain number of rules that you get to customize. And you get to control what those rules are, but it checks against those. So the easiest thing to do is just actually show you how this works. And I'm going to take that block that I created a little bit earlier, and we'll do some of these evaluations on it. First, we'll do costing. So we'll take this part, and I'm going to choose one of these templates right here. That's not the one I want. We'll choose this metric one here, and it's going to come back and give me some cost information. So here's my cost down here, and I can compare, and you can see the current and previous, and I can set baselines and stuff like that. Material cost is all information that goes inside of the template. I can put my total number of parts I have here. If I wanted to add additional stock for machining on different faces, I could do that as well. And then what it does is it goes through, and based on that information that it finds in the part, it calculates the setup operations that need to be done. In this case, I need 3 setups to do the different operations that I have. And then it also the load and unload time. So here's my load and unload times, because I might need to flip the part over if I'm only using a 3-axis machine or 2.5-axis machine to cut this part. Then each of the items, each of the features in the part actually gets calculated, and it calculates a time and therefore a cost. And then each of the holes as well. So each of those holes then get their cost associated with it, sums it all up and gives me a cost. So it's a nice little tool that allows you to come up with cost information for your part as you go. And then you can continue to add features and compare the cost as you go as well. Now, as far as design for manufacturability, we have DFM Express, which is really just a wizard tool that says, I'm going to run my wizard against this part right here, and it goes through and it compares a bunch of different design for manufacturability rules. Things like fillets on the outside edges, are they the right size? Standard hole sizes. In this case here, hole depth diameter ratio, it says it failed for two of the items. And it highlights them on the screen and it gives me a little call out letting me know that, hey, the depth to diameter ratio is 3.4 where the recommend is 2.75. You might want to change the hole size. You might want to change the thickness of your part to accommodate for that. But at least you know ahead of time these are things that might be watch-outs when it comes time to send this thing out to the shop and have it manufactured. So these are things I think you need to think about as you go through. And I think the SolidWorks Costing and DFM Express are great tools for that junior engineer who hasn't had as much design experience as some of the others, or some of the other guys who've been dragged out on the shop floor. Next thing we want to talk about is refining your product or change. Change is good. You know, everybody says change isn't. Change is hard, but change is good in the design process. You need to be able to leverage that good design intent and make robust changes to your model so that you can iterate it and perfect your model. The more you change it, you know, not always, but you can use that change to highly refine your product. But once you make all these changes, you got to make sure that you control those changes, and we do that with Enterprise PDM. With Enterprise PDM, you can securely store your files. You don't have to worry about version control because Enterprise PDM takes care of that. It takes care of that behind the scenes. You always have access to older versions if you wanted to roll back to those. You want to be able to share. So multiple people working on a project at the same time, different people are going to need to have different access to different items, but everybody wants to work on the assembly at the same time. So you may not have access to certain parts. They might be worked on by someone else. Enterprise PDM controls that. It also allows you to share information, search for information. So it's been said that engineers spend 20 to 30% of their time searching for information, and a lot of that is spent searching for the right file that they want to use, you know, the right part that they want to use. Well, with SolidWorks Enterprise PDM search capabilities, it's a very, very fast way to search on that robust information that you place into your parts. And then finally, workflow to route your designs through a process that your particular company may have. It may be an ECO process, or maybe an analysis process, or a purchasing process. Everybody along that path is going to be notified, and it has to follow certain criteria until it's met. So that's the Enterprise PDM workflow capabilities that are available. So let's talk a little bit about change and workflow and how we might use that. So our part looks pretty good right here. Our assembly looks pretty good right here. But maybe what we want to do is we want to have a little bit more range of motion. We want this foot to lift a little bit higher as we run it through its range of motion. One of the ways to do that is actually maybe move this hole back so that that distance that this throws brings this up a little bit higher. So what do? We make changes. Because we've captured that robust design intent in our model, we can simply come in here, click on a dimension like this, and we'll make that say 35 millimeters, and we'll rebuild that. Well, that's not too good. This link is kind of too long now, so let's change this link. So this one, we'll shorten this up. Actually, before I do that, I want to point out some things in Enterprise PDM, because I actually have this part checked out. If I undo this checkout, maybe I don't have permissions to make a change to that part. And I click on this and I go to change that, SolidWorks Enterprise PDM warns me. It warns me, hey, you don't have this part checked out. You don't have permissions to make this change. So at that point, I can come in here, check that part out. Now I have those permissions. So now I can change this to say 50, rebuild our geometry. You know, that looks pretty good for what we want. Now when I lift this up, you can see it lifts up much higher, maybe gives me a little bit better access to my workpiece, placing my workpiece in my model. So that's pretty good. So we talked a little bit about Enterprise PDM, whether or not I own parts, and I can then take this part that I've made a change to and check it in, and then I have established a second revision. Now, another way to look at Enterprise PDM is in the actual vault itself. So what is this Enterprise PDM? What is this vault? It's nothing more than Internet or Windows Explorer. So this is Windows Explorer. Everybody's used to looking at Windows Explorer. These are nothing more than folders. These are nothing more than files in folders. I can click on each of these items here, and I can get access to a preview. So I can get a preview of those. If I really wanted to get a deeper look at it, I could actually access e-drawings and kind of rotate and zoom around and see if that's the part I really want to work with or use. But all this information is available. If I have an assembly, I can see what it contains. What are all the parts that are associated with that? If I have something like this part, where is that part used? It's used in that hold-down assembly, and that assembly is used in the drawing. So all that information is captured. Even things like our hand sketch that we used, I can view that with our viewer, but I can check that information in. I might have several iterations of this that I might have gone through, and then I can have the versioning information captured for that. Things like a Word document, something like this right here, which is, you know, maybe some technical publications that show how to use this particular device. That information can be stored in there as well. So all that information gets captured with Enterprise PDM, and I think everyone should be controlling their information that way. Finally, the last thing I want to take a look at is how can you leverage, what are the ways to leverage your solid models downstream? That can be leveraging for photorealistic renderings. That can be for technical communications for, you know, these types of Word documents like we have here. That can be for CAM, for rapid prototyping. That can be for, you know, a variety of things. But you should take advantage of that solid model and use it downstream in those applications. So let's take a look at this Word document here. I'm just going to open this up. This is obviously Microsoft Word, nothing more than that. But it is nothing more than a kind of a document that might walk through how, you know, this thing, how you might use it. Here's the quick action clamp. These are the different items. This is how you use it. You also have some information over here that shows here's our sliding base. You can slide this out and provide more support for your workpiece as well. So these are images, nothing more than images. Where do these come from? Well, they came from SolidWorks Composer. Here's another document over here, which is basically just a parts diagram. Those are things you can create with SolidWorks Composer as well. So I'm going to open up our miter saw in SolidWorks Composer. Take a look at it there. So one of the things you can do is change the backgrounds. You can change, you know, zoom in, zoom out on this model, play around with it, get the right rotation. But all you're doing is kind of creating an image of how you want your model to look. I've created some already here, and these are images that I may want to use for my exploded diagrams that I need in a document. Here I might want to show how the clamp works when it's up. And you can see I have different rendering methodologies. All that rendering is done to match the type of rendering that technical illustrators would use. So, you know, I can, you know, create just kind of a flat design. I can do the silhouette like we had in some of our other ones. I can do smooth with outline. You get all different types of things. But the great thing about this is this leverages that SolidWorks model. It reads the native SolidWorks model and allows the technical illustrator to not have to bother with the engineer and not have to bug the engineer to say, hey, can I get another view here? Can you open that up? Can you change this here? Give me another view. They can create all this content themselves, and it's very simple and easy to use. Here we go. Down here is our two basically views that we created of the miter saw that show how the quick release clamp actually holds a workpiece into place. So it's, you know, you can add all these labels and everything to it. These can be smart. They can hyperlink to other parts if you wanted as well. In this case, I'm just creating images. You know, you're going to explode things and move things around very easily, and you don't have to worry about messing up the engineer's model. So it's kind of a nice, easy tool to do that. When I'm all done, all I need to do is send these out as high-resolution images, and then those are high-resolution vector-based images, so you get very good, clear quality images that you can then leverage downstream in Word or any Adobe products if you're creating those to create your technical publications. So some really cool tools to leverage your downstream models with SolidWorks Composer. So some of the things you can do, you know, assembly instructions, product manuals, marketing collaterals, renderings, and things like that. And the thing that I like the most is it frees the engineers to do their engineering work instead of having to work with the technical illustrators to, you know, try to get exactly what that technical illustrator wants to do. So in a short period of time, I ran over a little bit. Sorry about that. The key things that you probably should remember is, try to make sure you capture as much design intent as you can. Validate your performance of your parts, using the simulation tools. Constant manufacturability is something you should think about the whole time. And then don't be afraid of change. Change is good. Change is a way to make your design better and more refined, and control that with in the PDM environment. And then leverage your model downstream for things like photorealistic rendering for marketing and product manuals and 3D printing and things like that.